So again, welcome everybody to Paleo Talks. We're coming to you from the Center of Excellence in Paleontology at East Tennessee State University in Johnson City, Tennessee, where we're continuing to do these talks to bring paleontologists together and to bring our science together and get it out there to the public. And joining us today, besides Mauricio, is Chris Widga, as usual. Hey, Chris. And we also have Josh Samuels with us today, and I think Keela Redehoft is also on there, and they may jump in with some questions as well. I'm Blaine Schubert. I'm the director of the Center of Excellence, and it's just a huge honor to have Mauricio on again. If you don't know about Mauricio, you probably have seen his art, even if you've never seen Mauricio. His art is all over the place in terms of paleo art. I'll do a little advertising for him right here. In that this is it's probably backwards, but this is his book, Sabertooths, and that's what we're going to talk about today. He's a researcher and a paleo artist, and he really is known for bringing these animals back to life. And so as paleontologists, we are always looking for those people that can help bring these animals back to life in our imagination. And Mauricio is at the very top of this group of people. And so again, thank you, Mauricio. And if you wouldn't mind just going ahead and starting out by telling us a little bit more about how you got into doing paleo art and paleontology as a researcher.
Yeah, well, prehistoric animals fascinated me ever since I was a small kid. So I had this dream of when I grew up, I would like to work in something related to prehistoric animals. But as things went, I got my formal training in fine arts. So for several years, that was what I did. I painted surrealist oil paintings. I did my shows in art galleries. But I always wanted to pursue my vocation. So it was a series of coincidences that allowed me at some point to meet some of the leading paleontologists in Spain, and they were open to collaborating. So that allowed me to jump from that fine arts career to finally embracing this mixture of which I think it has the best of two worlds, art and science. So I started working for exhibitions in museums, and Spain was very much a tertiary period country back in those years. So that helped me to get centered in fossil mammals, because most of the fossil sites that were active belong to the age of mammals. And that suited me well because I love mammals. So then at some point, some of my paleontologist friends encouraged me to really turn some of our investigations about anatomy and reconstruction into formal research. So that's how I started to write papers. And so that was like 2-3 decades ago. And it still goes on.
And I don't think I mentioned that, you're coming to us from Spain, and where, you're working from your home right now because of COVID, but you also do research at the museum there. And what's the name of the museum there?
It's the Museo Nacional de Ciencias Naturales, National Museum of Natural Science here in Madrid. And I work with the paleobiology department. So it's a privilege and a lot of fun.
Excellent, excellent. Well, if you can go ahead and move forward and pull up your presentation, share your screen.
Okay, so I will try to do that.
So again, Mauricio has worked with all kinds of different paleo art, but certainly sabertooths are one of the animals that he's particularly well known for and has a book out on them.
Yeah, so sabertooths, yes, they are my favorite prehistoric animals, and I'm afraid that doesn't make me especially original. because saber-tooths are probably one of the most popular extinct creatures. And I think that much of that popularity is related to the impact and the influence of images, of reconstructions, because that's what the general public sees more than just the fossils or the bones. So it is us paleoartists that create these kind of images. So today I'm going to talk to you about the saber-tooths from the perspective, from the viewpoint of a paleoartist. But first, let us define what is a saber-tooth, because in the popular mind, it's almost identical with Smilodon. When people think saber-tooth, they think Smilodon, which is the popular saber-tooth cat from the Pleistocene of the Americas. We can see here in this slide, on the left, the skull of a Smilodon in different views. On the right, we see reconstruction, live reconstruction of a family of Smilodon somewhere in California. But the fact is there were many more species of saber-tooths. And there were very different kinds. And so what did they all have in common? What makes every saber-tooth a saber-tooth? Well, to start with, of course, having a pair of enlarged canines. Well, I will show you later. And besides those enlarged upper canines, they had a host of adaptations, anatomical adaptations in the skull and in the mandible, and also in the postcranial skeleton, that allowed them to use those upper canines for biting and killing their prey. But besides the saber-tooth cats, there were many other kinds of saber-tooths. So let's take a look. First, let's introduce the saber-tooth cats. They are the most familiar kind of saber-tooths. They belong in the modern family Felidae. So they belong in the same family as modern cats. And one example that we see here is Promegantarium. It is a very, very close relative of Smilodon, but there were many more genera and species starting in the early Miocene, middle Miocene, until the very end of the Pleistocene. And you can see in the phylogeny on the left of the image, the position of the felid family, the cat family, among the many families of carnivorans. But of course, they were not the only kind of saber-tooths to exist. So we have the Barbarophilids. They were another family of carnivorans that developed in parallel as a form of convergent evolution. They also developed saber-tooth adaptations. And the animal that we see in the reconstruction, Barbarophilis freakai, was a very extreme example of such saber-tooth adaptations. For years, it was thought that these animals were very closely related to cats, to true cats, and that is the position reflected in the phylogeny on the left. So you see it's the second group from top, Barbarophilidae. But most recently, some new data from the fossil record are suggesting that the Barbarophilids were actually more closely related to the ninrabids. And then you ask, what are the ninrabids? Well, they are yet another family of totally extinct carnivorans that also developed saber-tooth adaptations. So the ninrabids were older, they evolved earlier than the Barbarophilids or the true cats. So most species live in the Eocene and the Oligocene epochs. And they included a lot of genera and species. Some of them had only very moderate saber-tooth adaptations, but others like Eusmilus, which is the species shown in the reconstruction, developed really extreme saber-tooth adaptations as early as the Oligocene epoch.
Mauricio?
Yes.
On that photo there, or on that image that I'm sure you did the paleo art on, the teeth, all of those incisors, they look so pointed, canine-like. Is that something that's distinct to this group, or I remember seeing it a little bit in some of the Smilodon, but not to that degree?
Yeah. Okay. It is common to many kinds of saber-tooths to develop incisor batteries that are projected in the front, so that they are way ahead of the upper canines, and then they are very clearly crossed, and they the lower incisors become caniniform, and the lower canines become more like incisors. So it's like they are all pointed, and they can really grab a piece of flesh very effectively. But that is not the case in all saber-tooths.
And that's not something we see in living felids either.
Not at all. Not at all, because in modern felids, you have large upper canines and large lower canines, and they bite against each other, but the incisors are tiny, and they are arranged in a row. And the row is essentially between the canines. So that's very different from saber-tooths, where the incisors tend to project forward in an arch.
All right, thank you.
Yeah. So these three families we have been seeing are all members of the Carnivora, the order Carnivora. But there were other saber-toothed mammals that were not carnivorans. And here in this image on top, the top right, you can see Macaroides. And this was a saber-toothed creodont. And creodonts were a separate order, now totally extinct, which developed adaptations for hunting and eating meat before the modern carnivores did. And if you look at the phylogeny on the left, the creodonts are the second group from bottom. So as you can see, they are seen as closely related to carnivorans, something like their sister group. But then when we look at the other animal in the reconstruction, the one in the bottom image, this is Thylacosminus. And as you can see, it's a very extreme, even bizarre saber-toothed animal. And it was not a carnivoran, it was not even a placental. It was what we would call a marsupial, more precisely a metatherian. And if you look at the position of the marsupials in the phylogeny on the left, you see they are at the top. It's the group at top. You see how far removed it is from all the other animals that we have been seeing this far. And yet, in a totally independent, convergent way, it developed saber-tooth features. So with all this range of different fossil animals, we have the raw material for the paleoartist to reconstruct these saber-tooths as living animals. Now we are mostly working with anatomy. So in this image that I'm showing you, you can see from left to right a summary of the process of reconstruction, which always starts with the fossils. So on the left, you see the skull of the Sabertooth cat Megantarium, a true cat from the Pliocene, and in different views. And I used those views to model a digital 3D model of the skull of Megantarium. And in the center of the image, you can see two the renders of this digital skull, which I use to help me to draw the living head of the animal in any angle that I wish. And finally, you see on the right side of the image, the final reconstruction. But in this summary, I am omitting an important part of the process, which is the reconstruction of muscles. So we can see it here in this slide. This is Smilodon again. So we see the complete skeleton, which I have reconstructed by studying the shapes of the joints. The shapes of the articulation areas of the bones are what tell us the relative angles of each segment of the skeleton relative to each other. So by looking at those joints, we can assemble the skeleton in a lifelike posture. Then we can start to reconstruct the muscles from the inside out. And what we are going to use as a guide to reconstruct those muscles are the attachment areas of muscles on the bone. So layer by layer, we reconstruct, we see that the three successive stages until on the bottom right, we see the whole muscular mass of the animal. So I feel confident about this stage of the reconstruction because it's so strictly based on the morphology of the bones. But then we have to continue to the next stage, which implies a lot more speculation. Because when it comes to the most external features, like the sternal ears, the nose, the lips, the fur, and for instance, the coat color patterns, we usually don't have any direct evidence in the fossil record. So what we need to do is to combine phylogenetic and adaptation reasoning. So in terms of phylogeny, if you remember the previous slides where we saw the position of the Sabertooth cats, they are true cats, and their closest living relatives are, of course, the cats, but also the hyenas or the genets. So we look at those animals in order to borrow the most primitive and widespread coat color patterns. Then we have to choose, for instance, in the case of a Smilodon, between different options, and then we think in terms of adaptation. So if some species of a Smilodon are supposed to have lived in forests or in wooded areas and to be ambush predators, it would make sense that they retain the primitive spot pattern that is widespread among many of their living relatives. But if other species of a Smilodon probably lived in more open areas, it would make sense for them to lose those spots in the course of evolution and develop a more plain colored coat. Then it is time to set our creatures in motion, to reconstruct locomotion. And for that, again, we are going to combine different data. So we are going to look at their modern relatives to see the way they move, and then we are going to look at the anatomy of the fossils. So in this case, when I wanted to reconstruct a Smilodon running, I used as a reference my own photographs of a huge male lion galloping in Africa. I made these pictures many years ago. And one thing that strikes me from this picture is the impression of mass, of musculature. And that is in part because this lion, when it was galloping, always had at least one, and in many cases two, even 3 feet on the ground at the same time. That visually is sending us a message. This is a very heavy animal. So I decided to borrow this posture for my Smilodon. And one step I followed is when you look at this image on the lower right, you see a schematic drawing of where the bones would be located inside the living animal. And with having that in mind, I go to the next stage, and I draw the skeleton of a Smilodon. You see the image on top, and I arrange the different segments of the skeleton in the same angles as in the modern lion. So I am borrowing the posture, but I am obtaining a very different image because the relative proportions of the skeleton of Smilodon are so different. So we have the short, sloping back, almost like a hyena, with the relatively short hind limbs, and at the same time, the very powerful forelimbs, shoulders, and the neck. So I'm combining locomotion information from other animals with an accurate representation of the relative proportions of the fossil. There are some aspects of locomotion, of the reconstruction of locomotion, that require more attention to detail. For instance, were Sabertooths plantigrade or digitigrade? Well, for Sabertooth cats, Smilodon and Homotherium, some experts have proposed that they would be plantigrade. So in this image, you can see in the top row, Homotherium skeleton and life appearance as a digitigrade animal. And in the bottom row, the same animal, but with a plantigrade stance, especially in the hind limbs. So it is very different. So we need to be careful. And in the case of Sabertooth cats, a detailed study of the foot bones reveals that they were most likely digitigrade. Even if the angle between the feet and the ground would be more or less inclined, they were very likely digitigrade. For other saber-tooth carnivorans like Barbarophilids or nin rabbits, it is partly an open case as yet.
Mauricio, if you could just comment for a moment on the importance of understanding the anatomy of the living and even doing dissections to accurately reconstruct these, because I think that was one of the biggest take-home messages for us here when you visited, was just how much work you put into understanding the actual anatomy.
Yeah, yes, because when it comes to making this kind of decisions about will we show the saber-tooth as plantigrade or digitigrade, really the key is to understand how this or that detail of the osteology of the anatomy of the bones, which is all that is preserved in the fossil animals, relates to soft anatomy aspects like tendons and muscles, which are in turn what keeps the skeleton together in a lifelike posture. So in order to reach this kind of conclusions, it's not enough to just turn the fossil in your hands. You need to study the modern relatives, and you need to put together this anatomical evidence from dissections. So you look at the modern animals from the outside in, and to the extinct animals from the inside out. So I don't know if you are hearing this noise from,
it's okay.
from the...
We can hear you just fine, Mauricio.
You hear me fine? Okay, because there are some people working outside the home, and it's a bit loud. So anyway,
no worries.
Okay, so let's take a quick look at one of my favorite places in the world, which is the fossil site of Batallones here in Madrid, not far from my home. And it was discovered in the early 1990s, and it has become one of the most important references about saber-tooth cats in the world. So it's a series of cavities of late Miocene age, and several of these cavities operated as carnivore traps. And that means that today we are finding more than 99% carnivore fossils in these accumulations. And the result of that is that we now know very well the anatomy of some of the earlier species of saber-toothed cats, which before the discovery of this fossil site were only known from a few jaw fragments of maxillary fragments and isolated teeth. Now we have every bone of the skeleton of these animals. So the saber-tooth that we find in Batallones are Machairodus, the larger skeleton in this picture. It was about the size of a tiger or a lion. And the other kind of saber-tooth was Promegantarium. It is the smaller skeleton, about the size of a small leopard. So these two animals were sharing the ecosystem, and they had slightly different niches. So Promegantarium, because of its anatomy and because of its smallish size, was a proficient climber, and it would climb very efficiently, and that helped it to seek refuge from the attacks of its larger cousin and other large carnivores in Batallones. And then Machairodus was the king of Batallones. It was the dominant large carnivore there. And as you can see in this reconstruction, which is based on all that wealth of anatomical information from Batallones, it was rather, I would say, very cat-like, because it still had, it still retained many aspects of the generalized cat anatomy from its ancestors. So it hadn't gone too far down the road of saber-tooth specialization. And if we look at the skull of a very specialized, very derived saber-tooth cat like Smilodon on the left of this image, and you compare it with the skull of a lion on the right side, you can see that besides the development of the upper canines, which of course is huge in Smilodon, much more than in Machairodus, there are also other parts of the skull and mandible that are changing. And one of them is the mastoid area near the ear opening. And you see the mastoid process is huge in Smilodon compared to a rather small mastoid process in the lion. And this means that the action of the neck muscles inserting on the back of the skull was very important for saber-tooths, not only for Smilodon. And if we look at the hypothetical sequence of actions that allowed saber-tooths to bite the throat of their prey, in this case, we are seeing the skull of saber-tooth cat Megantarium, we can see that the whole head of the animal is moving to help the upper canine to penetrate into the flesh of prey, to damage all those blood vessels. And so that requires the action of neck muscles, especially at the beginning of the bite, when the jaw gape is so huge, more than 90 degrees. And one thing that we see in batallones, where we have every vertebra of the neck of Machaerodus, is that already at that early time, the neck of Machaerodus resembled the necks of more derived sabertooths like Smilodon or Homotherium in being very elongated. Here we can compare the neck of Machaerodus on top with the neck of a tiger at the bottom. So each vertebra was bigger, longer, and it had bigger processes for muscle insertion, for muscle attachment. That helped the animal. If we look at the different groups of muscles that insert, that attach in each of those areas, we can see how they could help the animal to bite its prey. We can see it more clearly in a live reconstruction of the sabertooth killing its prey. Because as you can see, while the cat is trying to pin down a large prey to the ground to keep it under control, it needs to position its head at a very precise angle so that it will bite the throat where the damage to the blood vessels would be greater and produce a quick death with a very short time period for the prey to thrash around and potentially hurt the predator. So there are other aspects of animal behavior that go beyond the movements, the motions of the individual, and that have more to do with their ecology and with their social behavior. So were some of the sabertooth species social animals? Well, there are evidences pointing in that direction. But if we look at modern cats, we can see that even within a genus, within the genus Panthera, we have animals that look very much alike, and we couldn't tell from their fossils which of them are social and which of them are solitary. So the lion is social, the tiger is solitary, and their skeletons are certainly, whatever difference they have, is not pointing in that direction to show us a difference. So it's very difficult to make inferences. And for that reason, I try to be cautious when I imply social structure in my reconstructions. So here we see a group of 4 adult-sized Homotherium. And well, one possible interpretation is we are seeing a mother with 3 grown-up cubs. I have seen groups of tigers more numerous than this. Say an adult tigress with her 4 big cubs following in tow. So, okay, it's like a calculated ambiguity. But if you ask me, I think that very likely Homotherium would be a social animal. Finally, let me take a quick look at the relationship between sabertooths and our extinct relatives, the fossil hominins. And because the Sabertooth cats got extinct so recently, there was a long period of overlap with our own ancestors. So for the first few millions of years, hominin species were mostly vegetarians, and they fit very well in the niche of prey. So like this Australopithecine, looking warily at Dinophilis sabertooth eating its prey, our main emotion would be fear. We would admire their power, but we would really be afraid of them. But then, as members of our own genus, Homo, evolve into ever more powerful, socially organized creatures with an ability to use weapons, it was more and more possible for us to actually chase a saber-tooth cat away from its rightful kill and snatch the meat. So there is indirect evidence that that is exactly what we did for many thousands of years. We almost became kleptoparasites. We would pester the saber-tooth cats to try and rob them of their prey. So there is evidence suggesting that our ancestors had an influence on the final demise of the saber-tooths in many parts of their distribution. So today we are again in that situation. Now it's the living relatives of the saber-tooth that are in danger of going extinct because of our huge influence in the ecosystems. So now it's not so much that we are robbing them of their prey, but we are taking their living space from under their feet. So it's the saber-tooth fate and the modern cat's threat. So that's essentially what I wanted to tell you. And I don't know if we are arriving to the time of questions, or I have wrapped up too soon.
No, that sounds great, Mauricio. We have a lot of questions that are coming in, and we definitely won't be able to even answer all of the questions. So let's get started on those. Thank you for the wonderful talk, and we'll go to David and see if he can hit us with a question or two.
Okay. Sure thing. Yeah, I'm glad you said that, Blaine, because I was about to say the same. We got tons of questions. We will absolutely not be able to get to all of them. So apologies in advance to everyone whose questions we don't get to. Mauricio, that was a great talk. I'm going to start. We have two questions, actually, that we're both early on asking about Barbarophilids. Can you talk a little bit more about where Barbarophilids fit and what? It sounds like that's been changing recently, the idea of where Barbarophilids fit on the cat family tree. Can you talk about that?
Yeah. So Barbarophilids evolved in the, well, I suppose, late Oligocene, early Miocene. Their early fossils are found in North Africa and in Europe, and maybe they evolved in Asia. So at some point they invaded North America in the middle late Miocene, and that's where the most spectacular species evolved. But for some reason, well, their fossils are not very common anywhere, so they weren't recognized as a different thing until the mid 20th century, and then they were described as a sub family or a new tribe of Sabertooth cats. But then with more studies, the opinions changed, and they were thought to be like a tribe within the ninrabbits. And that was the consensus back in the 80s or something like that. And then somewhere in the early 2000s, a new study of the dentition of Barbarophilids led to the idea that they were very closely related to true cats. And that's what is reflected in this phylogeny, which I took from my book, Sabertooth. But that was 2013. And in the meantime, new fossils have been found. So there is a study of a beautiful skull of Barbarophilid from China, which came out earlier this year, which has a very well preserved ear region And it was the study of the ear region that led to the conclusion that we probably have to take it back to its position as a close relative of the Nile rabbits, and certainly as rather separate from the true cats.
All right, thank you. David, you have another one?
Yeah, we've got another question that was asked, multiple people asked about how Sabertooths were using those incisors. So were they using them for dragging prey, for carrying things, ripping and tearing like canids do? What can you say about that?
Yeah, there is a diversity of incisor morphologies in Sabertooths. So, okay, if you see Smilodon, for instance, the upper canines are of course huge, but the upper incisors look smallish in comparison. So it's almost reminiscent of modern cats in that respect. But still, they are arranged in a moderate arch, some way ahead of the canines. But in other saber-toothed cats, in particular in Homotherium, those incisors were huge. They were arranged in a very clear arch, and they were working, they were biting each incisor between the lower incisors. So it seems like they had a more important function in those animals. So, and also in Homotherium, the upper canine is more fragile than in Smilodon because it's very thin. It's very flattened laterally. So probably the action, the combined action of the lower incisors, upper incisors, and lower canines allowed to grab parts of the prey, to control the prey, while keeping the upper canines relatively safe during early interactions with the prey, which is in fact what happens in modern animals that chase their prey, like hyenas or wolves. Their incisors are big. You see a grading from a smallish central incisor as you go out, and then you have a big third incisor on the side, and those incisors are arranged in an arc. So when these animals are nipping at their prey during the chase, the are not entering too much into the. So now finally, when the prey is under control and they are really going in for the kill, then the canines have are much more important. So probably all this huge incisor battery was used by some saber-tooth taxa more than others for initial contact with prey and to save the canines just for the killing bite. And one interesting thing is that when you look at the patterns of wear in the canines, the upper canines are almost intact in relatively old animals, where all the other teeth are fairly worn. So it looks that for each animal they killed, they only used their upper canines once. And that was for penetrating the soft flesh of the throat. So you have specimens of saber-tooths where most teeth are ruined, but still their upper canines are like new. So here the important thing is the diversity, so that there was clearly more than one way to use that combination of incisors, upper canines, lower canines, during the kill and during feeding.
All right, thank you, Mauricio. I have one that came in from Larissa DeSantis to my phone. How do you begin how do you begin to reconstruct extinct animals like hyenadon when they are so different in body proportions from extant taxa, with really large heads and smaller bodies, for example? How do you begin to reconstruct their locomotion, body size, etc.?
Yeah, as I mentioned before, the only thing that really gives us like a guarantee that we are true to the identity of the animal we are reconstructing is to start with the fossils. So each reconstruction has to be crafted from the inside out. So we start by putting together the skeleton, and that is defining the personality of the animal. So if I'm reconstructing a hyenadontid, I will borrow probably the posture from modern animals, and not necessarily only carnivorans, because while we see hyenodons as wolf-like, some aspects of their skeleton are more pig-like. They had these huge heads, and they were hanging from their necks. They had rather stiff vertebral columns. In that, they resemble pigs to some extent, but that is something the skeleton is going to shape for us. So I think the key thing here is not to let our imaginations fly as to how this animal would look, but stick to the fossils and let the successive layers shape. And then, of course, we need to look at the details. And again, we go to the plantigrade, digitigrade question, because giant hyenodons like the old world Megistotherium or Hyenailuros, they were huge animals. They were far heavier than a polar bear. And so I remember having this exchange of letters with a British paleontologist who had described he was Bob Savage. He described the skull of Megistotherium, and I proposed a reconstruction based on other hyenodons. And of course, the animal was digitigrade. And Savage said, well, but you know, the animal was so huge and heavy that I doubt it would be digitigrade. And I thought, sorry, but we have complete skeletons of Hyenailuros, which was just as big and heavy. And because these animals had feet that in a way resemble ungulates more than, say, cats, there's no way they would be plantigrade. So it's these small details that help us be confident about the creature we are building, like bone by bone, from the inside out.
So Mauricio, this is an example, what you're showing right here, of something that was interpreted wrong, but can you think of any examples where something was described just based on a little bit of material and then paleo art was developed around it, and then it dramatically changed when a full skeleton was found?
Well, no example comes to mind right now, but generally, whenever we have to reconstruct something based on very fragmentary remains, I follow a guideline, a rule of thumb, which is I will only reconstruct this animal if we have reasonably close relatives that are more complete. Because otherwise, I will feel so frustrated about what I am doing that I really don't feel any confidence. So whenever I have been offered to reconstruct something out of just a piece, I I prefer not to do it. And one exception was when I was reconstructing the fossil animals from the site of Lothagam in Kenya. I enjoyed that assignment enormously because there was a complete skeleton of a Homotherium relative called Locotunjailurus and some other incredible carnivores. But the reason why a monograph was being written and why there was money for reconstructions for that site was because there were hominid remains there. And those hominid remains were only a few isolated teeth with some fragment of mandible. And we had no idea what the complete animal would look like. So we talked about this with the experts, and we decided to do, instead of the Cheshire cat, the Cheshire hominid. It would only be a smile. It's like in Alice in Wonderland, the Cheshire cat, which is just a floating smile at times. So this was a smile in the dark. So we could only see, from behind some branches and leaves, a dark shape, because apes are generally black. So it was black in black, and you could only see the teeth as the animal was smiling. So it was a humorous solution to the dilemma of should we show the full body of the animal? I said, sorry, I'm not going there. That's why I'm not reconstructing the Denisovians.
Right.
Let's go back over. I suppose they would be similar to Neanderthals, but don't hire me to do that job.
We better go back over to David and try and fit in a few more of the Facebook questions.
Sure. We've got an interesting question here from Maggie, who asks, what is the reason for different saber lengths between species? Why are the saber teeth long in some species and short in others?
Yeah, that's a very good question. And of course, we don't know, but we have hypotheses. And there is this idea of ecomorphs, like a morphological complex associated with an ecological niche, and that there have been attempts to apply this to sabertooths. So the idea was proposed that they were one kind of sabertooth, not dependent on the taxon, but on the adaptation, that had very long, curved, thin sabers. Those were the Dirk-tooths. And those would include, of course, Smilodon and many other many other members of extinct families, like the Barbarophilids, extreme Barbarophilids, or extreme nymph rabbits like Eusmilus. These are all Dirk-tooths. They have very, very long upper canines, not necessarily serrated. And it was supposed that these were solitary animals, ambush predators, and they would kill very large prey relative to their body size. And then we would have the scimitar-toothed cats like Homotherium. And here you see that the upper canine of Homotherium is not very long, or to be more technical, not very high crowned, but it's broad. It's very flattened, and it has strongly serrated margins to its sabers. So Homotherium and some of its relatives, like Macharodus, they had relatively long legs, so they were better runners than Smilodon or the other Dirk-tooths. So it was supposed that these animals were hunting different kinds of prey with a different method, and nice theory. The problem is that the only scimitar tooths to have existed belong to one particular clade, which is the Homotherium tribe within the Sabertooth cats. So it's not so clear that this is a taxon-free ecomorph. So we don't know, but at any rate, what I would suggest is that the relatively low crowns of Homotherium canines are related to the extreme flattening. So if you get such a very flat canine and you make it even longer, as long as a Smilodon, it becomes too fragile. So maybe that some of the Sabertooths that had very, very flattened canines, which had a huge penetration power, and they had these serrated borders for cutting, they couldn't get much longer because they would become fragile sabers and easier to break. So the sabers of Smilodon are not too thin; they are really relatively robust. So that could be one reason.
Mauricio,
yeah,
we're getting close to running out of time. Let's see if David has another one or two he wants to try and squeeze in.
Sure. I'll ask this one next. This question from Facebook is, given the capacity for sociality, is it possible Sabertooth cats might have possessed manes like, modern day lions or other unique social displays?
Yeah, it's absolutely possible. But here it's where the imagination of the paleo artist is constrained by the concept of the widespread features. So the male of the lion makes perfect sense in its social system. And that's something that we see a posteriori, because we have already seen that the lion has a male. This is something absolutely exceptional among all the species of modern cats. So if we reconstruct Smilodon or Homotherium with a male, we are creating like an association in the minds of the viewer, because it screams, lion, this is a lion. So we would have to be, and maybe conceive of some other external feature, external sign of dimorphism. And on the other hand, let's remember that Sabertooths in general were not as extremely dimorphic as lions or even leopards are.
All right. Blaine, you if you have any final questions, or if Mauricio has anything left to say?
Yeah, I think we should wrap it up. We were having a little bit of sound issue there too, right at the end. But no worries, Mauricio. We've got a lot of questions answered. And if you wouldn't mind answering some of those questions afterwards, that would be great as well, the ones that are on Facebook. If we didn't get to them, we apologize. It's just been wonderful to hear from you again, Mauricio. Thanks again for coming on to the show.
My pleasure, as always. Thank you.
All right. We'll see you next week, everybody.